Okay, so I wanted to speak about soil chemical weathering and soil conversion, because we will see that in the Hillslope processes, having material which has been already weathered and transformed into smaller particles makes a difference in terms of the Hillslope physical erosion processes that will be acting on the Hillslope. There are three forces basically that can move your particles. When I say particle, it can be a block, metric block, so it can be a piece of sand, a grain of sand. First force is the gravity. You will have also some reaction of the ground onto the particle. So one normal force we are not interested in, and one component parallel to the surface, which will be the resisting force, which are friction force, that will maintain in some way the particle in place and get opposed to gravity. And if you have a fluid, in particular water, you can have a third force, which will be mostly the driving force of the drag force related to the differential motion, or which is proportional to the differential motion between the fluid and the particle. So we see that we have resisting force and potentially one or two driving force. So on the Hillslope and on the landscape, I mean, when you are above the fluvial network, so in that part, the main driving force will be gravity, and once you arrive in the fluvial network, you will get both gravity and fluid action or drag force, and the further you go downstream and the gentler is the gradient. Obviously, the main driver when you arrive in low gradient river is just the fluid action, and gravity has no effect. There are many different Hillslope erosion processes, and we can make some kind of category going from the small scale processes that we will call diffusion processes, that can be impact of raindrop, action of vegetation, bioturbation, so it can be due to vegetation, it can be also due to burrowing animals, even the worms are doing some job. It can be also some freeze-thaw alternations due to a cycle of freezing. Then you go slowly, you go through some different category of processes, all involving mostly gravity and with longer and longer distance of transport, and obviously the largest one, the largest scale one, are the deep-seated landslide that can go up to granular flow or debris flow that can have distance of transport quite long, of a few kilometers. So we go from very superficial processes that will be displaced material over a scale of a few millimeter or fraction of millimeter and small volume, and we arrive to processes that can move up to almost cubic kilometer of material over distance of several kilometers potentially. So Hillslope, I forgot to translate, so Hillslope of diffusion processes on the Hillslope. So for example, you can have rain splash. So what happens with a rain splash? You have here a raindrop arriving on the surface, and if there is no vegetation and loose soil, then you can have a small impact, and you will send material on both sides, here in 2D. And normally you will send more or less the same quantity of material on the right side than on the left side. But because of the slope, you see that the distance traveled by the right particle, ejected particle, will be longer than this one on the left side. So it means that if you multiply the raindrop and the rain splash, so there is more efficient on longer distance of transport on the right side than on the left side. So at the end, you will have some physical transfer of the material to the right just because of the longer distance of transport downslope than upslope. Same with a freeze flow as a cycle of dilatation and contraction of the soil. So it's a phenomenon that you can have in clay stone by hydrating the clay. So when you put water, the clay will inflate, and when it dries, it contracts. And you will have also the same when you have a cycle of freezing. So what happens when you get the soil which is freezing? Because ice is taking more space than water, then you will get some expansion. And the expansion of the soil will be perpendicular to the soil surface. So you have this vector here of expansion. And then during the day or during a summer, you will have the heating of the soil. So there is disappearance of the ice, so contraction. And during this contraction, you don't contract reversely, but you are guided by gravity. So the contraction is following the gravity line. So you have this trajectory, and the net difference after a cycle, it's a small vector in the direction of the slope. So you have a small flux of material, QS, and if you have n number of cycles of freezing, then after 1 year, you will have a net flux of material, which will be proportional to the tangent of the angle of the hill slope. So this is directly the slope. So we can see in this process, but it can be seen also at first order in this process, that there is a direct correlation between the sediment flux at small scale and the slope of your hill slope. The higher or the steeper is your hill slope, the higher will be the flux. So for that reason, it is called a diffusion process, because we will see that we end up with a diffusion equation that describe the motion of or the displacement of the erosional product on the hill slope, and diffusion equation which is similar to, for example, the diffusion equation that is used classically for heat diffusion, heat transfer. Again, I forgot to, no, the flux of material transport downwards is proportional to the local slope. So it's what we saw just previously. And if we applied the law of conservation, so we can say that the change of elevation of the hill slope will be equal, well, if you have uplift, to some uplift turn, and mostly to the divergence of the sediment flux. So if we introduce this expression of the flux as a function of the slope into this mass conservation equation, we end up with the change of elevation of the hill slope, so the first derivative over time of the Z, the elevation of the hill slope, is proportional to the second derivative of the elevation. So we see typically a diffusion equation appearing, and this term of this coefficient is called a coefficient of linear diffusion. So we have an equation describing the evolutionary slope, so we can have the question in mind. So what's going on in such or such situation? So for example, what kind of landscape can emerge from in steady landscape affected, or in steady hill slope affected mostly by diffusional processes? So let's consider stable interfluves, or a stable small river, and in between an interfluve, so some hill slope, rising over some continuous uplift from below, and we try to understand the steady state shape at the end. So if you have steady state, this term is equal to 0. So we end up with the second derivative of Z is equal to the uplift rate divided by the diffusional coefficient, and integrating it, we end up with a relationship Z is a function of mostly the horizontal distance at the square. So this is the equation of a parabola. So it means that the equilibrium shape of an interfluve, if the hill slope is affected only by diffusional processes, so the final shape you expect is some kind of parabola. So you can see here the equilibrium shape, and in this parabola the medium part of the crest is relatively flat, and it's steepening more and more when you arrive close to the river network. So it can be shown in this kind of model that, for example, the relief, so the difference of elevation between the crest and here, will be proportional to the uplift rate divided by the diffusional coefficient. The maximum slope that will be found here, it's also depending on the uplift rate. So if the uplift rate is increasing, you will increasing the steepness of your parabola. And same for the mean slope of all your watershed. It will be also increasing linearly with the uplift rate, and also depending on 1 over the diffusion coefficient. If we apply a coefficient of diffusion of 0.01 to 0.001 square meter per year, then we can show that, for example, applying this relationship, the mean uplift rate and mean erosion rate will range between 0.1 and 0.01 millimeter per year. So do we observe in nature this kind of landform? So this is a picture from the Appalachian Mountain on the eastern part of the North America. All mountains, I don't remember, they were formed during probably 200 to 300 million years ago, and they have been slowly eroding. And now the erosion rate are relatively low, so we can suppose that most of the hill slope are eroding by small-scale diffusional processes. And you see, indeed, that in between the fluvial network, you observe some rounded topography with minimum curvature and minimum slope at the top, and increasing slope when you arrive close to the drainage network. I think in the previous day, someone asked me how we determine the diffusional coefficient. So it's one way that can be done here. If you consider a terrace riser, so let's say a topographic, I already qualitatively draw in the previous day the evolution by diffusion of this terrace riser. You can see that if you take again the equation of the diffusion equation that drive the evolution of your Hillslope, if you consider here the terrace riser evolution, there is no uplift in that case. So the uplift term has vanished. We have just this equation, and given the boundary condition and the initial condition, we can have an analytic solution where the elevation is evolving according to x and to the time, following this equation with Earth, which is the error function, which is the integral of a Gaussian. And the slope will be following a Gaussian function, means some nice bell-shaped function. And the further, initially you will have a slope like that. So imagine your terrace riser. So initially the slope is a square shape, and then slowly and slowly you will have your bell shape will be having a wavelength increasing. So this kind of evolution driven by this equation. So once we know the evolution of our riser, and that we have been documenting the evolution both of the wavelengths and on the steepest slope at the middle part of your scarp, then you can go on the field and measure with a topographic instrument the shape of your riser. And you can either compare the topographic you have been measuring, so the dot, the cross, with the theoretical model given by the previous equation. So you can compare either the topography or the slope. So you can see here from the slope that we indeed follow, almost except in that part, follow some kind of Gaussian shape or this kind of shape. And this amplitude is giving you the product of K, the diffusivity coefficient, multiplied by the time. So if you know, because you have been dating the terrace, for example, T3, so you know when the initial riser was created, so you know the time. So in that case, you have been able to measure Kt because of the wavelength of your Gaussian. You know the time, so you can derive the diffusivity coefficient. So it has been done in different settings. Southwest USA, so it can be on terrace riser or on marine terrace riser. It has been done in North California in slightly more humid environment. California, Southeast Australia. This example is from Tian Shan, relatively arid, and the rate which has been found goes from 1/1000th of square meter to, let's say, 1/100th square meter per year. So this range of value.
Jérôme?
Yeah.
One query in this kind of scenario, that would be how to constrain the initial geometry of your riser. So we have to approximate the initial geometry, and then we have to model the diffusion, and then
this
is your final geometry.
This solution is given for an initial angle of 90 degrees. So for a straight step or square step. In most cases, there is some initial angle which can be 60, 50 degrees or 40 degrees. So in that case, there is also an analytic expression, but that incorporate also the initial angle. I'm trying to remember. In theory, you could try to fit your topographic profile by playing both with KT parameter and also with initial angle. I would say that when you begin to have a significant diffusion, so maybe not here, but likely more, then the initial stage, it's almost vanished, and it doesn't make a big difference if you had a vertical cliff or a cliff at 50 degrees. But in the initial stage, in the initial evolution, yes, it makes a difference. So if you start from something which was 50 degrees or vertical, if you don't know that there is a risk, if it was 50 degrees and you assume a vertical, that you will be overestimate probably, you will overestimate the age by this way. So what people do, I'm not sure, but I think it's depending on the type of material, but it's really, the material of your terrace is really loose material, loose alluvial material. So the initial slope is only governed by the friction angle, and you can consider that the initial angle of your riser was around 40 degrees, or 35 to 40 degrees. If your material has some cohesion, maybe you can have some riser slightly steeper. But definitively, I mean, I'm not sure. The most reasonable thing is probably to start from 40 degrees, because even if initially you have something nearly vertical, then very quickly you degrade it by another process than diffusion. At least for that part, it will be mostly collapsed by small landslide. So because it is a process much more efficient and much faster than diffusion, so probably this early phase of evolution of your riser is very quick, and it doesn't matter for the final age estimation. So I would say that the most reasonable assumption for the initial slope is around 35 and 40 degrees. So then you have a small scale diffusional processes, and then when you increase the slope, you begin to increase the efficiency of the Hillslope processes, and also the efficiency of the effect of gravity. So if you have larger distance of movement and also larger volume involved in this movement. So you can have some feature of solifluction like that, or here. You can have also some shallow slide where there is just shallow soil stripping. So it's, I think, an Hillslope in California. So you see the small strip of the material. So volume of a few cubic meter or less than cubic meter export over a distance of a few meters. You can have also at depth some kind of soil creeping. So again, some smaller, slightly smaller distance of traveling. So typically, it's marked in the landscape by the fact that, well, artificial structure like poles will be tilted, and you can see it also in the trees by the fact that the trunk is twisted, because if there is some soil creeping, then the tree begins to tilt, and the tree doesn't like to be tilted, so it will try to grow by following again the vertical. So for that reason, you can observe this kind of curved tree trunks. And in terms of relationship between erosion rate and the mean slope, so remember when we look at the steady state shape of an hill slope dominated by small-scale diffusional process, we end up by saying that the mean slope is expected to be proportional to uplift rate, and at steady state is the same as erosion rate. So we expect a linear relationship between the mean slope of your hill slope and the erosion rate. And when you look at the erosion rate documented, for example, by barium-10 in quartz, as a function of the mean slope, we see this kind of increase. Up to value of 20-25 degrees, there is a general linear relationship between the erosion rate and the mean slope. And when we arrive to value of 25-30 degrees, then the data begins to depart from this line. So what does it mean? It means that oops. Well, I will fix it later. So it means that here you need to have a diffusion coefficient much higher or much higher to get more efficient process in order for a given slope to have higher erosion rate than predicted by this linear increase. So in that part, we'll begin to speak about nonlinear diffusion to be able to keep pace with this increase of the erosion. So what the reason for the fact that the erosion rate stopped to increase linearly but increase faster than linearly with the slope? There are two reasons. For high slope, the gravity effect is becoming more prevalent. And the second thing is when you increase the erosion rate, then in order to evacuate the material by diffusion, so rain splash, bioturbation, you need to have, in all these cases, you need to have soil and disaggregated material. So you need to convert bedrock into soil at the same rate, at least, than the erosion rate. Because if the rate of erosion is faster than the soil conversion rate, or bedrock to soil conversion rate, what happens? After some time, you will have removed all the soil, and you will have a naked bedrock, and the bedrock cannot erode by rain splash, cannot erode by burrowing of the gophers, or this kind of thing. So, you can have diffusional processes as long as you are able to produce soil enough quickly to be brought to the system. If the erosion is faster by the soil conversion, then you need to begin to export fresh bedrock, so it can be broken material or large block of material. So you switch in some way in terms of process. When you increase the erosion rate, so soil production rate is here. So we saw it was probably, well, historically it was considered to be limited at a value of 0.1 millimeter per year. And above this value, people were considering that soil production rate was not fast enough to produce material that can be removed by diffusion processes. So we needed to, I don't have it, we need to involve deeper phenomenon to remove the material by erosion, and deeper phenomenon need a material removed at the level of the substratum of the bedrock, like landslide, in particular deep-seated landslide that involve both soil but also fresh or relatively fresh bedrock from below. Sorry. Probably I missed some slide. So as I was mentioning earlier, this view that there is some limitation in soil production rate that limit the action of diffusion processes has been recently challenged in two studies. So one by Imzas and co-author, they documented soil conversion rate up to 0.3 or 0.4 millimeter in California, and still more recently in New Zealand they have been proposing soil conversion rate above 1 millimeter per year. So very fast conversion rate that permit export of soil at such a rate by physical erosion. But to my knowledge, it's the only two studies that have been documented very high production rate permitting high superficial erosion rate. So basically, for value in between, let's say, 0.1 and 1 millimeter per erosion rate, so the threshold is maybe not very well defined, but above this value, people consider that superficial erosion is not possible because there is not enough soil production rate. So the only process that can permit large erosion rate will be deep-seated landslide. So in terms of landslide, there are many studies on this kind of object, mostly because of the natural hazard involved by landslide. And there is, again, a large categorization of the different landslides. They can be characterized by the rate of movement. Some are rapid landslide, other ones are slow landslide. And they can be characterized also by the form. Some are translational landslide, some others are rotational landslide. So for example, this one, you can see the zone of sliding is curved, so we will be speaking of rotational landslide, and in that case, it's more like a layer which is falling apart along a plane, and we'll more speak about translational landslide. So you can have landslide and mass movement at any scale and involving water or not. So we can recognize dry rockfall, so just from the cliff. So you will get some blocks that detach and fall apart. You can have rapid landslide. So one example in Nepal, it was in 2014. So during monsoon, it was triggered by heavy rainfall. You get all this mass that fall down into the river. But you can have also slow evolving landslide. So it's one landslide in France. So you see the Hillslope, which is fracture. And there is, on the next slide, 10 years later or 8 years later, you see an opening slightly more important. And then 10 years later, a motion by several tenths of meter, so much more important. And then it begins to fall down. So a slow motion over more than 30 years. So when there are very slow evolving rock slide or landslide, like the previous land, you can see in the literature the notion of what we call deep-seated gravitational slope deformation, or DSGSD. So it mostly relates to a large scale or large amplitude, large volume rock slide that can involve all the hill slope. So you can see this on this picture. It goes from the crest in between the fluvial network. It goes from the crest and goes down to the base of the hill slope at the level of the valley. This kind of slow motion is characterized by intense fracturation of the massif, and you can have several kinds of fracture. Some will be more or less parallel with the same sliding motion as the main fault, as the main fracture, and you can have also antithetic fault that will develop some scarp at some kind of scarp sloping opposite to the slope. So we'll speak about anti-slope scarp. So for example, here you see an example. You have in Himalaya a crest somewhere here, and this scarp developing as an anti-slope scarp related here, or it will be more in this case of figure. So the fracture, the main fracture is developing an anti-slope scarp on the opposite side of the valley. In the literature, you can see this kind of scarp affecting and fracture affecting the massif by the name of sakung also, that correspond to the opening of fracture, usually transverse to the relief. So you can see different type. You can have a double crested mountain, so with an opening of a small fracture defining a small rift at the top of the hill. You can have a series of parallel fracture. We can speak about toppling in that case if the blocks are falling apart the one after the other one. And you can find also this kind of fracture associated to some kind of differential lithology with a strong unit over a softer unit. And it can be observed both on Earth, but even, it means, for example, on Martian landscape. So this kind of feature can be active today. So we can see here some opening of a fracture associated to this kind of slow landslide. And some of them have been documented because of the, they have been documented by geodesy. So some of them show, for example, an acceleration of the motion in the recent times. Some other, like this one in Norway, show some long-term history over more than 16,000 years. 16,000 years of motion with rapid motion, and for the last 10,000 years slower motion. So it's some rock slide that can evolve relatively slowly. And in some cases, after this slow motion history, then it can be some acceleration and some global collapse. So in that case, you can have any kind of geometrical collapse, so it can be the crest, the wall crest that collapses down into the valley. That can be some progressive toppling of the blocks. That can be the cliff that again fall down like that. So any kind of situation. So you can have slowly moving rock slide that became a rapidly moving landslide in some cases. This kind of object, the DSGSD, they have been documented, so they're very large rock slide. They have been documented mostly in the Europes and the North America, and you see that there is almost nothing documented in Himalaya, well, according to both authors. So we can ask, is there no such a kind of object in the Himalaya, or it is a question they have not been documented? So for my experience, I have seen several fractures like that, so like the one I just showed you previously. So I presume that there are many also, like in other mountainous regions, many of these big fracture hill slope, a big DSGSD in Himalaya, but they are still to be documented. What controls the stability of slope and the occurrence of a landslide? So for engineering purpose, for people looking at the threat and the gravitational hazard, they are used to define what we call a factor of safety for a given hill slope or for a given landslide, which is the ratio between resisting force, so the friction force along the fracture plane, divided by the driving force, so mostly the weight of the volume of the rock slide or of your hill slope. If the factor of safety is above 1, it means that your hill slope is stable. If the factor of safety is lower than 1, it means that the driving force are much important than the resisting force, and it means you get collapse. So either a slow-moving collapse or rapid collapse. And the friction or the resisting force is driven by static friction and usually is documented through the use of Moore-Coulomb criterion. So that involves a cohesion term and a coefficient of friction. So for most rocks and weathered rocks, whatever it's carbonate, granite, schist, whatever, this friction angle close to the Earth's surface, so at low pressure is around 0.7 to 0.8. So it corresponds to an angle of friction of around 40 degrees. And if you have clay within your fracture, maybe this friction can be lower. So we'll see in the afternoon that we can, using Moore-Coulomb criterion and very basic equation and very basic 2D description of the hill slope, we can show that the relief of the hill slope will be, if I draw, do I have the graph here? No, I don't have the graph, sorry. So if I draw some hill slope, and I consider the elevation of the hill slope and the angle of your hill slope, then we can show that it is shown that the higher is the hill slope, the lower is the angle. And in fact, for very small relief, so a small cliff, like here a 20-meter cliff, you can have locally vertical cliff, 80, 90 degrees steeping cliff. But when you have very high relief, several hundred meters, then you begin to have much lower, much gentler slope, and you try to go toward a value constrained by the friction angle. So if your friction angle of your material is around 35, 40 degrees, for large hill slope, the maximum stability angle will be 35 to 40 degrees. Otherwise, if it's steeper, it will just collapse. There are two factors that can govern also the slope of the hill slope. First, the pore pressure, because in Moore-Coulomb equation, if you replace the stress normal to the fracture by the stress minus the pore pressure, so what we call the effective stress, then in that case, if we reduce this term, then the shear stress of the friction is lowered. So for a same angle between dry and wet material, so with pore pressure, that it will be easier to have a collapse for a given slope. So the associated elevation here to a given slope will be lower in case you have a lot of water in your massif. And same for the dotted line here. If you have an acceleration due to seismic, then you increase the driving force due to gravity during if you add some acceleration term, and then you will be also lower the stability of your topography. So the effect of the earthquakes and the vertical and horizontal acceleration on the hill slope is obvious after an earthquake. So I think this picture corresponds to a picture taken after 2005 Kashmir earthquakes. You can see numerous landslides. In 2005, after the Sichuan earthquakes, you can see also on this Landslide image, when you compare before and after the earthquakes. So this is a red color through Landsat image. So the red color corresponds to the vegetation. And you see that the clear spot here corresponds to unvegetated part, just the place where the vegetation has been stripped away by landslide. And I didn't put the author of this paper. I think, I don't remember exactly who was it, but it documented the extent of major high density of landslide after these earthquakes. And you see there was a majority of landslide very close to the thrust fault. So during the earthquake, you get 2 thrust fault activated and one northern part which was more activated with a dominant strike slip motion. So here, mostly vertical motion, and here, mostly horizontal motion due to strike slip. And it's really where you got some maximum vertical acceleration linked to the seismic event that you get more co-seismic landslide. So I was mentioning this issue about the maximum angle that can reach the hill slope, because it is governed by the friction angle for high topography. And if the rock has the same, or the rocks in a region have the same friction coefficient, you will expect exactly the same slope for your landscape everywhere. And it's what was been documented by Burbank in '96. So he looked at the northwest syntaxis of the Himalaya at different region. Some of them, like the Nanga Parbat region, is affected by very high denudation rate, several millimeters per year. And some other region, like here or here, are affected by lower denudation rate and probably lower uplift rate. So if it will be just diffusion process, we would expect where we have high denudation rate to have high topographic slope. When we have low denudation rate, we have low topographic slope. And in fact, looking at the histogram of the slope of this different region, it was observed that all these regions have exactly the same histogram, with some maximum value between 40 and 60 degrees. And the interpretation of that, it's all these regions are dominated by hill slope processes, and because, by landslide processes, and because landslide processes are governed by the friction angle, then whatever is the denudation rate, whatever is the uplift rate, then the slope is governed by this limiting friction angle. Another place, in Santa Cruz Mountain in California, again, the expression that we get planar hill slope governed by the friction angle. So this common feature of a single maximum slope angle is not observed everywhere. So, for example, in this study in the Himalaya, it was observed that if you go north of the range, the Himalayan range or south, then the maximum and even the mean slope angle are not the same. They are decreasing southwestward and in accordance probably with the annual rainfall. So where you get more rainfall and in general you are at lower elevation and slightly higher temperature in the southern part of the Himalaya, the mean slope angle is lower than at high elevation north of the range. So one explanation is because in that part you get temperature higher and also mostly higher rainfall. Then you get also deep weathering of your fracture, and if you get deep weathering, maybe you can have some clay minerals in your fracture, and that might significantly decrease the friction angle of your fracture. So that might explain why the mean angle and probably the maximum angle are also lower in that part, where you get more precipitation. So landslide processes are governed by slope, this critical slope ID. They are governed also, we saw, by seismic activity and also by pore pressure. So if it's governed by pore pressure, we would expect where we have period of higher precipitation that you can activate a little more landslide than when the climate is drier. And it's what it has been proposed both in the Himalaya and in the Alps, looking at large landslide, documented the activity by using, for example, barium-10, as I shown yesterday, measuring the age of exposure of the fracture of the slow-moving landslide or the rapid-moving landslide. For example, in the Alps, it was documented that many landslides occurred around 10,000 years ago, so probably just after the last deglaciation and receding phase of the glacier. So we got some phase of decompression of the valley, and the second phase of activation of the landslide was around 4,000 years, and probably during a phase where the climate was documented as more humid than today. Same here. It seems that many landslides documented in the northwest Himalaya occur during period of more intense monsoon. So in both cases, it seems that there is some kind of synchronicity between the activation of large landslide and the more humid period. What happened to the material of the landslide when it collapsed for rapid landslide or rock slide? So the material can travel over distance just the size of the hill slope, but sometimes they can travel for longer distance. So it can be either a granular dry flow, like so north of the San Bernardino mountain in California. You see the initial landslide somewhere here, and this large lobe of deposit that travel over kilometers as granular flow. And if you have water in your system, it can be water coming from the glacier, it can be water coming from the lake or from the intense precipitation, then you will have more like debris flow type motion. So this kind of competent flow with a high concentration of sediments moving large block and making potentially large imprint in the landscape or in the bottom valley with quite erosive event. In the Himalaya, what about the dominant erosional process? So I gave already some hint about the issue in the previous day. So we are mostly eroding by the landscape by landslide. There are at least 3 arguments to do that, to say that. First one, we saw that the soil production rate worldwide is, in most cases, lower than 1 millimeter per year. We saw on the crest of the Cooley Valley that's probably from Barium 10 around 0.01 to 0.1 millimeter per year. So soil production rate is not fast enough to produce fine material to be transported by diffusional process. So first argument, well, it seems that the only process that can remove denudation rate of 1 to 3 millimeter per year, it's landslide or deep-seated landslide. We can have also two other kind of arguments. One looking at the sediment budget or the landslide budget, and the other one at chemical signature. So back to the cunicola. So I will show it just in a few slides here. In that part, there is a large active landslide, which is regularly activated during monsoon time and produce a large amount of sediments. And you can see here during the rainy season, during the monsoon, this is the main river coming from here and that drain this landslide. The water is completely brown because of the heavily loaded in sediment. And there is a small tributaries coming from a vegetated basin which is not affected by landslide. And you see that the water is completely clean because all the hill slope are protected by the vegetation. So if you don't have landslide, you don't put sediment into the river and the river is clean. So first qualitative argument and more chemical arguments. If we compare the sediments, the suspended load coming out from the basin, so if we analyze the sediment, whatever it is during monsoon or outside monsoon, suspended load or sand, we get in terms of geochemistry this ratio of the sodium over silicium versus aluminum over silicium. So this is mostly this ratio which is interesting, which gives us an idea about the weathering of the material. So if the plagioclase are weathered, then the sodium will be depleted, otherwise no. And when we compare the sediments of the river transported by the river to the potential source, the two potential sources can be the soil, if you have pellicular erosion, or it can be landslide. So in red, you have the chemical signature of this landslide, and in orange color, the chemical signature of the soil. So obviously the soil are depleted in sodium because of the weathering of the plagioclase. And you see, is it okay? No? No more battery. Anyway, I will speak. Yeah. Soil in terms of sodium content. And if we try to invert these two walls, so the soil and the landslide, we end up with the sediment representing, made of more than 90% of landslide materials and less than 10% soil material. So second argument to say that landslide dominates the sediment phase and the erosion. Another possibility is to look at the landslide and to see if the number of landslide and the volume eroded by the landslide correspond to the flux of sediment we measure downstream. To do that, people usually compare two sets of satellite images. So for example here, we have a satellite image in 2002. We set of aerial photos to get some activation of landslide. So we can count on all this area. You can count so either manually, so looking from place to place, or now the people begin to develop some automatic computerized system to count the difference of vegetation that can be seen between two sets of photos to count automatically the landslide. There is still some difficulty. I don't remember if I put it here. Yeah. The difficulty is you see some strip vegetation, but you want a volume eroded by the landslide. The volume eroded by the landslide corresponds just to the scar of the landslide. But the strip vegetation, obviously it has been stripped from the scar, but because of the debris fall down, they have been also removing or stripping away the vegetation in the downstream part or in that part. So you can, if you just look at the change of vegetation, if you consider all that area, you will be overestimate the true surface and the scar. And if you want to have only the volume due to the removing the material, you need to count only this polygon corresponding to the scar. So sometimes it's important, either if you make some computer system to have some correction factor, or if you do it manually or visually, directly one by one, to be careful to identify the zone corresponding to the scar and the zone correspond to the debris piling. It's not always obvious to make the difference. Then you have a distribution of different area or surface of landslide, and to transform your surface into a volume, you need some scaling law. So there are several scaling laws in the literature. Classically, we get something which is close to a value of the volume of a landslide more or less proportional to the area or the surface of the scar to a power of 1.5. It means that the thickness, the mean thickness of your landslide is scaling more or less with the dimension of the radius of your landslide. Recently, it has been done by Mark and his co-author. So they did two things. They looked at different sets of satellite images to look first at the landslide triggered by monsoon over several seasons, and also in green, the landslide that has been documented after the earthquakes. So they correspond to the Gorka earthquake in 2015. So they correspond to what we call co-seismic landslide. So monsoon-triggered landslide, seismically triggered landslide. And they look at the distribution of landslides. So this is the frequency of occurrence of the landslide. So it can be in year per square kilometer. And here you have the area of the surface of the scar of the landslide. The largest one that are documented are around a little less than 1 square kilometer. So in blue, they are the earthquakes triggered landslide, and in red, the monsoon triggered landslide. So depending on what is the frequency of occurrence of your earthquakes, you can have a different value for this distribution. The important points here, it's by making the integration of all the volume associated to the large landslide, rare large landslide, and frequent small landslide, by integrating down to the largest landslide which has been documented in the Himalaya, that involve volume of more than 1 to 10 cubic kilometer, and with surface of more than 10 square kilometer. Then by doing that, taking the frequency of the giant landslide documented in central Himalaya, adding the contribution of co-seismic landslide and monsoon-triggered landslide, they end up with a value of erosion around 2 millimeters per year due to the landslide. And 2 millimeters per year, it's more or less the order of magnitude of the erosion in the central part of Himalaya, as measured, for example, from barium 10 at the outlet of the Narayani River. So this is a third argument to say that, well, even if there are large error bar, if we just consider the landslide alone, then we can account the sediment flux exported by the mountain or coming from the erosion of the Himalaya. So it's another argument to say that, okay, probably landslide is a dominant process in the erosion of the steep mountain like Himalaya. I will just show you an example of the Hillslope activity in the Himalaya. An example to show you that sometimes the evolution can be slightly complex, so that you can have several processes nested in the sense that I have shown several categories of rapidly, slowly evolving landslide, large one, deep one, shallow one. I will show you in this example that they are all interacting in some way. So I don't present anymore the Kudi basin in central Himalaya. And you see here this strip zone, and on the field you see this large eroded zone. So if you go on the field, you see 80 meters deep with deeply weathered and fractured material. And if you look at the foliation in that area, it has been rotated by 30 degrees relative to the normal regional orientation. So it seems that all that part has been sliding and rotating. So that way. So uphill we find anti-slope scarp that show that we get some very deep-seated slow rock slide or fracture like the GSD or deep-seated gravitational slope deformation. At some stage, all this hill slope just slided by a few hundreds meters, making the foliation rotated. And now, because of this intense fracturation of the material, it's very easy for the erosive action of a small stream to develop, and it's what we see. We have a small stream here eroding very aggressively this weathered and fractured material, and it produces this erosion and this erosion of the talweg, some further disruption, further fracturation of the material, and you see slices of material which are sliding, or you can see new fracture like this one, which initiated a few years ago and which is making the delimitation between the next slice that will be colliding or collapsing into the talweg. So a view of this kind of slice with a strip of vegetation still under weathered and fractured bedrock, which is slowly sliding, and the kind of fracture you can find on the field, so with one person giving the scale. So in this kind of mass of weathered and fractured material, so you get some very aggressive retrogressive erosion. So between 66 aerial photo and more recent satellite image in 2011, we can see the progression of the landslide that receded the Thalweg with small collapse by several kilometers in the direction of the crest. So in 66, rapidly developed into the 90s in that way. During 10 years, it was a quiet period, and then erosion reinitiated at the beginning of the 2000s and developed toward a more southern branch. And today there are more fractures that probably collapse in the few next decade. So we can track the evolution of the area. So it has been expanding continuously through time. And we can convert it in landslide volume loss, or rate of landslide volume loss. And you see there's two periods. The progression of the retrogression during the 70s and 80s toward southern western branch, some period without activity, and then for some reason the regressive erosion, the aggressive erosion, start again along the southern branch with very high rate of loss of material. So to understand this kind of object and what's going on, so we get this slice that collapse, sometimes that are sliding but a few meter or a few tenths of meter. So what happens to the materials in the on the slope of the Thalweg inside this big regressive erosion area? So in order to track what's going on, you can put, for example, camera. So there are camera for hunter that can take regular picture every 30 minutes or every minute. So in that case, we choose to take picture every 30 minutes to have a look on what's going on. And after that, you can analyze and make a choice of one good picture per day and try to make a movie of what you observe. So for example, we are going to look at more or less that part. So I don't know if it will be working. So it's a movie made with one picture taken every day, and from the May up to November. So monsoon is between 15th of June and end of mid-October in that area. Okay, it didn't work. Okay. So you see here the precipitation. So during May, there is not so much precipitation, and you begin during the monsoon to have large motion. But it's a slow motion. Every day it's moving by a few meters. So you have also active Thalweg with some stream, some water moving material, but the rest of the material is slowly moving that way. So you get some export of the sediment over the monsoon from the crown of the landslide down to the Thalweg, and then the river export the material further downstream. Oh, sorry. So then you can look at there is some small hydropower station further downstream. So you can there is a concrete dam here. So there is a monitor section where we can collect sediment and where we can also measure water flux. So in that case, for example, this is a record of the discharge in blue, and we install also a turbidity current to track the concentration or the turbidity of the water during monsoon. And by integrating this sediment chronicle over the monsoon, you can get a volume of sediments that go through your structure. So this is the equivalent erosion rate or sediment flux at the downstream part of the basin. And you see some history with relatively high rate. So we go from 2-3 millimeter per year of erosion up to 10 millimeter of erosion in the more recent year. And when we compare the activity of the landslide, so remember in blue the loss of volume or the propagation of the landslide, and in red and pink the suspended load, you see that, again, as claimed previously, most of the sediment in this basin is not coming from the whole basin, but it's just coming from one spot, this active landslide area. So when the landslide area is not so much active, you don't produce so much sediments, and when the landslide activity has been increasing, then you produce a lot of sediments that you can find in your river. I will skip that part. So conclusion, in Himalaya, we get many landslides, some of, like this one, rapid landslide due to monsoon precipitation, but as shown by Mark and his co-author, we get a significant contribution, maybe up to 50% to the budget of the co-seismic landslide. And obviously, we can have plenty of situation that goes from deep-seated rock slide to shallow landslide or rapid landslide, and we can have some complex situation with nested processes, as I shown in the codicola. So to end up with the Hillslope erosion, in slowly eroding landscape, mostly linear diffusion, parabolic shape due to this linear diffusion, then we increase the erosion rate. So because of a steeper slope, we begin to have nonlinear diffusion processes like shallow landslides, soil stripping. It means that we begin to have to saturate in terms of slope angle. So we stop to have a parabolic shape for the interflow between our two rivers. We still have at the summit some kind of parabolic shape, but the lowest part of the slope will be dominated by a critical angle in some planar slope. And if we keep on increasing the denudation and the erosion rate, the only process that can keep pace with such high erosion rate and high uplift rate will be landsliding. And because landslide is governed by the friction angle in some way of the material, then there is some asymptote or some limited critical angle, and you will see in this kind of diagram between erosion rate and mean slope some saturation effect, and whatever the erosion rate it is, you will get a more or less similar slope angle, and the traduction in terms of geometry of your slope, then you will get some kind of triangular shape. So you will go from rounded landscape to slightly more red landscape to triangular and planar faces. And in any place in the world, so I have shown yesterday in Himalaya, here in Southeast Tibet, you will always see more or less the same kind of curve between mean slope and erosion rate, so some kind of gentle linear increase, and then when you arrive around 25 to 30 degrees, then erosion rate can become completely independent of the mean slope. So contouring factor, first one, slope, obviously because of gravity. Second, climate, and also seismic acceleration. And remember, small-scale processes like diffusion are limited by the rate of conversion of bedrock into soil. Okay. Yeah.
So we are talking about co-seismic landslides.
Yeah.
So what is the minimum magnitude of those earthquakes? Like they are triggering landslides in that area?
There are a few scaling law you can find in the literature that relate the size of the earthquakes and the number or the volume of co-seismic landslide. So there are two factors in this total volume. The area affected by acceleration and the acceleration by itself. So obviously a magnitude 5 makes a low acceleration, so the effect is minimal, and the higher is earthquakes, or the magnitude of the earthquakes, the higher is the acceleration, so the greater chance is to get some landslide. But after it depends also on the litology, so I cannot tell you exactly what is the critical value. For example, in California, there are significant landslide activated after North Ridge earthquakes, which is a magnitude 6.2 or something like that. So I would say from 5.5 to 6, we begin to have some incipient, or we begin to have some significant effect of seismic acceleration on the activation of co-seismic landslide. But again, it's difficult to answer just about magnitude because the acceleration is depending on the magnitude, is depending on the depth of your earthquakes. If it's a very shallow earthquake, you will have more effect for a small magnitude, and it is also dependent on the site effect. And it has been proposed that, for example, on the crest, or depending on the orientation of the waves, you can have some amplification or de-amplification. And it was proposed that for co-seismic landslide, you can have, because of this amplification of the waves in the crest, a slightly more activation of landslide close to the crest than close to the valley bottom. Yeah?
So when you are trying to measure the basin-wide denudation rate in an area where you have dominant landslide, but not all over the places, like few places are affected by the landslide.
Yeah.
So when you are taking a sediment sample at the outlet, so there should be some mixed effect of those landslide and some other sediments which are generated due to the bedrock erosion process. So when you are interpreting the erosion rate, so there should be some mixed effect of both of the process. So how do you resolve these two things?
Well, either if there are some strong difference of litology in your basin, and you can make some provenance analysis. If you know, for example, you have two parts, one schist part and one limestone part, and you know that you have landslide only in the schist part. If you find some, I don't know, half carbonate and half schist in your sand, then you can say that maybe the landslide from are contributing only in the schist part, not in the limestone. So by playing with the provenance, maybe you can make a difference. But otherwise, if you don't have this kind of feature, I mean, you can do, as I was presenting for the small Himalayan basin, looking or taking sample in the soil, having the chemical signature of the soil. If you have landslide, you can go at the outlet of the landslide, take also sediment coming from the landslide to have the signature of the landslide. And if the signature, the chemical signature of the landslide is distinct from the one of the soil, then you can go at the mouth of your river, take the sediment, suspended load or sand, and make the chemical analysis and see if the chemical analysis is closer to the one of the soil or closer to the one of the landslide. So in that, it's in the example I presented, taking the average value, it was possible to make a budget and to calculate that in that case, because the sediment are close to the pole or the average value of the landslide, we can say that 90% is coming from landslide type or bedrock erosion or deep bedrock erosion rather than soil or superficial material.
So I have another question. So when you showed a Hillslope is getting diffused by diffusion process, you also have reverse downcutting, on the both of the side.
Yeah.
So it's kind of a moving boundary problem, like your both of the boundaries are not fixed. So at that time, your the diffusion process should also incorporate the channel incision process. So
I'm not sure to understand. You mean in terms of signature of the sediments?
Yeah. So
I mean, in that case, let's say, for example, we have we consider steady state. So this curve, it's for increasing its steady state shape for increasing uplift rate. So low uplift rate, steady state shape at intermediate uplift rate, steady state shape at high uplift rate. And so in that case, we consider that we have a steady state, so the river is downcutting at the same rate as the uplift rate. So obviously the river is your boundary condition for your system. That,
what is the controlling factor that determines whether a mass wasting process will be converted into either landslide or debris flow phenomenon?
sorry, what is the controlling factor for what?
If a mass wasting process, mass wasting material to be converted into a landslide or to be converted into a debris flow?
Oh. Well, first of all, you can have debris flow which are not involved by landslide. Like, for example, if you have a glacial lake outburst flow, because of a lake behind the moraine is emptied very quickly and bringing a lot of material from the moraine. So if it's a debris flow coming from associated to a landslide, it will be mostly depending on the initial water content of the on your setting. If there is a shallow landslide, not involving, or relatively shallow landslide, not involving huge quantity of material, and if it's during the rainy season, the river is bringing a lot of water, so you have enough water to mix with your material. So in that case, there is a chance you get a debris flow. If your landslide is arriving in a lake, also there is enough water to make a debris flow. But if, for example, it's a cost-seismic landslide, so it's not raining and there is no water available, then you can have only a dry granular flow. So it's mostly the main factor, it's the availability of water. So for example, in the early 70s in Peru, there was a massive debris flow in the Cordillera Blanca because there was a rock fall in the high summit, but that bring during its fall a piece of glacier. So after the melting of the ice and the mix of the water of the ice with the debris, then you had enough water to produce a debris flow. So it's just a matter of availability of water or not.
So does the grain size also controls the process? Like if there are higher amount of finer particles like clay or sand?
I would say that yes. I mean, if you have more fine sediments, I think both for granular flow and dry granular flow, but also for debris flow, it will be easier to move the mass. For granular flow, because it will be easier to have some kind of suspension fluid mix of fine grains and air, and for debris flow, a mix of fine material, some with water. That makes some competent fluid.
Thank you.
Hello, sir. You have said that the landslide is occurred by two processes. That is, one time monsoon when intensified, and the other is tectonically induced. So, how I can differentiate in the field that this landslide will be occurred by climate or this is tectonically influenced?
I don't know.
Or it is
I mean, it's a landslide. It's a mass of material that just fall down. So, if it's triggered by water, if it's triggered by earthquakes, doesn't make a difference. So, obviously, if you have satellite images, if you are studying something that occurred in the last few years, by just looking at satellite images, you will be able to see when your landslide occurred, and if during that meantime there was an earthquake, you can relate the moment of your landslide and the earthquakes. So if they are unrelated, it's due to water or to precipitation, probably, or if it's related to earthquake, you will see the temporal link. If you are studying an old landslide deposit, so you don't have any kind of information, you cannot do, it's not possible to do the difference. Statistically, as I was mentioning earlier, it seems that there are more earthquakes, more landslide initiated close to the crest than down to the valley during earthquakes because of the amplification effect. And it seems that the high precipitation of the Himalaya, the monsoon triggered landslide will occur preferentially close to the valley bottom, just because usually the water table will be higher in the downstream part than high in the crest. So, but it's just statistics. So, on average, there is more landslide in the downhill part for precipitation triggered landslide than for earthquake triggered landslide. But if you look at just one single event, it's this kind of statistical consideration is useless.
Thank you.
So in line with this previous question, so if like a triangle faces, you can delineate it on a satellite image, and we know there is a known fault through known geology, and also presence of lineaments along in the satellite images. So can we not plot the landslides as well in the satellite images, and you know that there is a present fault? So my question is, sir, will the landslide form at the base of the fault scarp, or like you said, in the higher relief, if it is earthquake triggered, at the crest and not at the valley floor?
I'm sorry, I didn't follow you.
The landslide can be mapped in the satellite images, and if we see there is a lineament or a previously known fault, So if that is repeatedly triggered, the landslide is repeatedly triggered, so can we not associate that landslide with the fault activity?
Yeah, probably. Again, it's depending on the situation. If you are speaking about recent feature, it's like, oops. Okay. So obviously, this is in some way the case here. If you don't know that there was an earthquake in 2005 and you have just access because you are living in the space, so you don't know exactly what's going on Earth in terms of earthquakes, but you can see from far away the occurrence of landslide. So in that way, you see a nice density or higher density of landslide along this mountain front. So if you have just this information, yeah, you can infer that it is related to probably some fault activity, because if it's just something produced by a storm, well, the storm will hit that part, or you would expect some kind of more diffuse distribution of the landslide. In that case, it's following a nice lineament, so it's very tempting to, if you don't have this information about the earthquakes, it's tempting to associate this density, high density of landslide with an earthquake. But now, if your questions in the past, if you just document old landslide, maybe if you can, and you say all the landslide are some way aligned or something like that. So maybe it can be related to an earthquake, but it's difficult to say, because if you have a fault, you have generally, well, if it's thrust fault, you have generally some activity that makes that you have steeper slope. So the steeper slope will be the primary trigger or factor that makes landslide. So if you observe where you have steep slopes, landslide can be due to the earthquakes, but can be due to just to the fact that you have steep hill slope, and when you get some more pore pressure, you activate your landslide. So it's slightly difficult to answer your question.
So in line with the same thing, like when you have repeated motion on a fault scarp due to uplift, so we have formation of a colluvium wedge. So does that have, is there a similar terminology for, or a similar stratigraphy observed in the repeated landslides? And if there was, so what, which dating technique could we use in that scenario?
Sorry, I'm not sure to understand exactly.
So, like if you have repeated activity on a fault scarp, so we'll have development of colluvium wedges.
Yeah.
So, and dating each colluvium wedge, we can get the activity with respect to individual earthquake cycle, earthquake events. So
Okay.
like,
Yeah.
if you have one landslide, it will produce
Deposit.
and if that landslide is reactivated, you will maybe have a subsequent deposition.
Mm-hmm.
So do we have such formation in landslide?
Okay.
And if there were, then what dating technique can we use?
Well, the same as for paleoseismology, as you were mentioning with colluvian wedges. I mean, each time you have a landslide deposit, there is a good chance to cover some vegetation, so you can have some debris. So you can date them with organic debris and C14. If at the bottom of your landslide deposit there was fine sediment, you can also date with OSL. Or in case there are very large landslide or massive rock slide, then you can get some, in some cases you can see the base of the fracture, and you will have what we call friction height. So it's the rock has been heated so much that it has melted, and you get some further fault, what we call pseudo-tachylite. So it's some kind of glass due to the melting of the rock. So you can date it with different technique, with a fission track, for example, or with thermoluminescence. So, but it's very big landslide. It's not the case you are mentioning, probably because you are interested by the deposition. So to go back to your idea, it's if we have several deposition like that, then yeah, look for organic debris at the base of each landslide to have because in between each landslide you will have a soil development. So you would expect a landslide debris, soil development, another landslide debris, soil development, and so on. So normally in the soil horizon, if it is preserved, you should find some organic material to date with C14. Obviously, if it's older than 50,000 years, there is no way. You have to find another way. But for example, with cosmogenic nuclides, it seems to me quite difficult. Except, well, yeah, except it's a very old landslide, so maybe you can do burial age with chlorine, with aluminum-26 and barium-10. But another point related to question, if you have something like that, so if it's just a landslide like this one, so then you will have some deposit. If it is like the case I presented in the Himalaya, where it's part of something larger, where the material is already fractured and weathered, then you can have propagation and several generations of landslide deposit, probably. But if it is not the case, if the bedrock is unweathered and not fractured, then you will have this kind of deposit, and the next landslide that will occur, there is more chance to get it laterally here or here, because once, I mean, here you have the soil, here you have the bedrock, which is partly a fracture and partly disaggregated, and here, the deeper you go, the less fracture and the less weathered fracture you get. So once you stripped away all that material by a landslide, then you arrive in some much less weathered and fractured bedrock. So some material which has a higher cohesion. So it will be easier to activate a new landslide laterally than here. So you will have to wait some time to make again some weathering, so soil production and also deeper weathering in the fracture, in order to reduce the cohesion of your material and to be able to activate a new landslide. So I don't know if you have in mind a typical example where you have several generations of landslide deposit, but I think except if there is some foreland basin, so you have permanent deposition, but otherwise, most of the time, you get, if you are in some mountain area, you get a landslide deposit, and before you get a new landslide above, most of the rock deposit have been washed away by the erosion of the river or whatever. So there is a good chance that this situation where you have a succession of landslide deposit is not so common. Oops.
how to map or study deep-seated slow gravitationally induced landslides? What is the different techniques that people use?
The different techniques, if you want to document the present evolution of your rock slide, it will be exactly the same as for fault activity. So people will be using GPS by putting different points outside of the rocks, the deep-seated landslide, and inside the zone which is moving. So tracking the displacement with the GPS. You can do also total station. People are also putting, if you want, a laser trigonometry to follow the motion. You can do also INSAR interferometry, or you can do also subpixel correlation by comparing different satellite image or aerial photo. So this is for the present deformation. You can also, people are also instrumenting, because some of these landslide, because they can evolve towards some more dangerous in terms of collapse. So they are slowly moving, and sometimes they can collapse. So at least in Europe, this kind of landslide, if they are close to habitation and close to population, they are monitored or densely monitored. So people track also some evolution of the fracture. So you can put seismic station to look at the micro seismicity linked to the opening of the fracture. You can track also some change in the chemistry of the water. So if there is some evolution of the water circulation into the fracture. So any kind of technique to look at that part, and for the recent deformation or the modern deformation. And if you want to look at the old deformation, so like the study I've shown, displacement 10,000 years ago, basically there are two techniques. The first one, if you see, do I have it? Where is it? As I've shown it yesterday on some example, this one is some kind of soft bedrock, but if it's hard bedrock and you see some nice, well-preserved scarp, you can do barium-10. You can do even along the scarp a vertical profile to follow the activity of the fracture. And you can do also paleoseismic studies like paleoseismic trench. So if you go there, make a small trench across some scarp and look at, for example, the colluvium wedge or the succession of colluvium wedge that you relay to some event. So, well, depending also on the behavior of your fracture, some fracture are sliding very continuously, sometimes with some acceleration phases. Some other one can slide by 1 meter, like a little like a fault. So if it's a succession of increment of displacement, then you will see something with paleoseismology technique, because each time you have an event like for an earthquake, then you will get a scarp with some colluvium wedge at the base of the scarp. If it's a slowly moving and continuous motion, then I'm not sure that paleoseismology will give you something, because you will get continuous accumulation without transition between quiet phase and more active phase. But in contrast with the barium-10, if you have a nice scarp, whatever it's continuous or it's by step, you will see some evolution through time. So there are the two techniques. On one side, to study the long-term motion, and for the modern motion with all the technique we have now with GPS or whatever. And the final point, it's you are also interested by the geometry and the depth of the routing of your system. So in that case, people will be using geophysics method, or surface geophysics. So it can be with a seismic station. So normally in the sliding mass, because there is more fracture, you expect a slower wave speed, or acoustic wave speed. It can be also with electric sounding or electric survey. Also because you have fracture, you have water circulation, the porosity is not the same. So usually you can have all the massif with higher or lower resistivity, or maybe just the zone of the fracture at the base. So by geophysics technique, there are also techniques based on the also on the seismic record, V over H. It's document also the degree of damaging, of fracturing of your bedrock. So it gives you also an idea of the more or less the intensity of the depth of the fracturing of your bedrock. So there are plenty of techniques.
So how to locate at the first hand, like area? How to locate a first area which is unknown? So how to find that thing?
Always feature. It's always geomorphic feature. So double crest, anti-slope scarp, like this one. So it's basically on the observation of the geomorphic trace of the fracture with the surface, but you identify something going on.
So active landslide and deep-seated landslide, they are two different or same? Like landslide happened and all the scarp came out.
Yeah.
I can see the difference between.
Yeah, you can have a continuity. It's there. Well, I would say between rapid landslide and slow landslide, or very slowly evolving massive rock slide, it's a continuity. So you have any kind of intermediate. Some landslide will evolve by a few millimeter or a few meter over 10,000 years, and some of the one will accelerate and collapse in just one shot. And in between, you can have rock slide moving by several tenths of meter per year, or
Okay. Then other part is denudation in Himalaya in other normal, it's like 2 mm per year, let's say. And now I found that this number is mostly because of the landslide. Because in that paper they correlate, I saw that it is also, landslide is also around 1 to 2 mm per year. Landslide, erosion because of the landslide. So now question is, when we say about denudation 2 mm per year in general, I think we think about a continuous process, like from last 1 million years, the denudation is 2 mm per year.
Yeah.
Now, after this paper, I found that it is not so. Like, it is not continuous. 2 mm per year is not continuous from 5 million years or 3 million years. So, in that case, so if landslide is the main dominating factor for contributing the sediment and denudation, then how can you distinguish a continuous denudation rate and a discontinuous denudation rate?
Well, if I understand well your question, it's more or less related to the point I was mentioning yesterday about cosmogenic sampling in sand. So obviously landslide, it's some kind of stochastic process. So if you consider 3 basins, in one basin you will have for a given period a landslide. In the 2 other basins, you don't have a landslide over that period. So if you just look at instantaneous erosion and sediment flux coming from the 3 basins, in the 2 basins without landslide, the sediment flux will be low, like the clear water I was showing in the Himalaya. And on the 3rd basin, obviously you will get a high flux of sediment and probably higher or much higher than the long-term denudation. So that's the difficulty. That's a difficulty both when you measure the sediment flux by just measuring or taking sample of suspended load and regularly in your stream. It's also a problem with cosmogenic nuclei in the sun, because in the landslide, in the basin affected by the landslide, there will be more sun coming from the deepest part, so maybe the cosmogenic concentration will be lower than the long-term average. And at the rivers, in the 2 basins which are not affected by the landslide, you will get only sun related to soil erosion, so with a concentration much higher than the long-term one. And so this is a problem for 1st order and maybe 2nd order. And when you go downstream and you integrate larger and larger basin, so the probability to have some good averaging of the different stochastic process related to the landslide is higher. So when you work on the large basin, like the Narayani one, 30,000 square kilometer, there is a good chance that you average this effect, and that even on a decade, the sediment flux you can measure is not very different from the long-term erosion rate. So it's just a matter of distance of integration. And but still, if you have a process that affects a very large surface, and this is the case for the earthquakes, for example, for the 2015 earthquakes. So then if you produce a lot of co-seismic landslide, then you bring into the fluvial network a lot of sediment. So potentially, just after the earthquakes, you could expect an increased sediment flux at the outlet of the river. In the fact, for some reason not completely explained for the moment, but after 2015, people have been monitoring the sediment flux, so during monsoon 2015, 16, 17, and 18, well, for the last years, and they didn't observe a real increase of the sediment flux. Well, the first reason, in 2015, the monsoon was very low intensity, so at least in Nepal. So even there was sediment available due to the co-seismic landslide, so the discharge in the river was not high enough to transport all the sediment. In 2016, the monsoon was pretty normal, and the sediment flux have been, I would say, 2 times higher than the normal, but it's not huge, just 2 times. And 17 and 18, we almost returned to some kind of normal state. So we don't know exactly what happened. Maybe people are speaking about the notion of connection. In order to have sediment exported by the river network, you need some connection between the Hillslope and the stream network. And so what's behind the connection issue? It's you need to have the material from the landslide going down to the river system. If you get a landslide and all the material moved by a few hundred meters but doesn't arrive down to the river system, that there is no way to transport it. The material is sitting there and slowly is revegetated, and you get just slope collivium, slope debris, and it's not participating directly to the instantaneous sediment flux. So it's one explanation why in the outlet of the big river draining the zone of the earthquakes, we didn't observe, or people have not observed some huge increase of sediment flux. Maybe if tomorrow we get a much larger earthquake, maybe the response will be different. Maybe the system will be much more loaded in sediment, but for the moment we don't know. Just to finish, sorry. This evening I will show an example for which probably we get some disturbance in the systems, and even a large river like the Narayani during a few decades or centuries have been exporting much more sediment than presently. So again, the question, what is average value? What does it mean? Do we have stochastic behavior, variation through times?
Okay, thank you.